Thank you. Well, thank you for coming. I come from the University of Lisbon, actually from the computer science department, and I'm collaborating with the physics department to analyze fusion data. So that's where we are getting at later in the presentation. So first, for those of you who are not very familiar with fusion, I would just like to, give a quick introduction. So fusion is actually the process that powers the sun. So if we look at the sun, what we see is this tremendous amount of energy coming out. I don't know if you ever thought about this, but how is that energy generated? The process is actually rather simple. So you have a very large amount of mass, right? Because the sun is much bigger than Earth. And this mass has a gravitational pull, right? And what happens is that at the core, matter gets compressed. And gets compressed so strongly that it heats up, of course, because when you compress something, it heats up. And heats up to the point that electrons are stripped from nuclei. Okay? So if you have an atom with the nucleus and the electrons, they just get stripped away from each other. And then it gets so dense that nuclei actually get very close. And if you remember anything from physics or chemistry, you know that nuclei have a positive charge, right? So they repel each other. The thing is that if they get really, really, really close, then suddenly they snap. They come together. And so this is, let's see, this is one of the simplest fusion reactions, and it's also one of those reactions that is taking place at the sun. So what you have in the left, it has these names that perhaps are not very familiar, but it's just hydrogen, okay? It's just two different isotopes of hydrogen. So this isotope contains a neutron, and this isotope contains two neutrons. So this is one of the reactions that happens in the sun, and actually it's one of the most interesting reactions for us, because if we ever think about doing this on Earth, for several practical reasons, this would be perhaps the best reaction to choose, okay? So, as I was telling you, if two nuclei get close enough, so to surpass the repelling force, they just snap. And there is a curious phenomenon, which is if you measure the mass of these isotopes, and if you add this mass of helium, so a nuclei with two protons and this neutron, then you discover there's actually less mass in the products than in the original ingredients. Okay? And this means, by the famous Einstein equation of E equals mc squared, this mass is converted into energy. And because mass is being multiplied by c squared, you can imagine that just a single reaction of this will release a very, very large amount of energy. Okay? So this explains how the sun is so strong and is our main source of energy. Okay. So since the 50s, last century, I mean, scientists have been thinking about how to reproduce the same reaction on Earth. And the problem is, we can actually heat matter. We can actually heat matter, I mean a small amount of matter, of course. We can actually heat a small amount of matter to the point that it fuses, to the point that we have nuclear fusion reactions. We can do that. It's just that, where are you going to place this matter? Because it cannot be in contact with anything else, right? It's so hot, and it's going to explode. So where do you put that? Can you imagine? Where do you put a slice of matter that is not in contact with any material? And it's still on Earth. Well, some Russian scientists in the 50s and 60s came up with an idea. So as I was telling you, the electrons get stripped from the nuclei. So once you have electrons and nuclei, you have charged particles. And then they had this aha moment when they thought, hey, if these particles are charged, I can hold them together with a magnetic field. And this was the idea that some Russian scientists had in the 50s. So their idea was I actually have two fluids, a fluid of electrons, they are free, they are completely free, and a fluid of nuclei, and they are completely free. Of course, some of them are negative, the electrons, and the other are positive, so they will flow in opposite directions, but it doesn't matter. It's just two fluids, and we can treat them independently. So they came up with this idea that of having the plasma, so that's what we call matter in this state, so of having the plasma confined by magnetic fields. And in the sun, you know that the sun is spherical, right? And in the sun, the plasma is being confined by the gravitational field, right? So that's a very easy solution, actually. But here on Earth, we have to come up with a more sophisticated solution. We have to confine the plasma with magnetic field, right? So they came up with this scheme of coils and currents and everything to create a magnetic field that keeps the plasma, running around and avoids the plasma from getting in touch with the walls. In principle, because you will see some results that I'll show later, and it's not that clear. But the idea is to keep the plasma confined and away from the walls. Well, since the 50s, several of these devices have been built, and more devices are being built as we're talking today. So the largest device that is currently operating, it's in the UK. It was the result of an European initiative, okay? Of course, everyone today is worried about Brexit. What's going to happen? Are we going to lose JET? Are we going to be unable to send scientists there? Well, I think things will be all right. But currently, this is the largest operating tokamak in the world, okay? There will be an even larger one in France. So that's nice. But currently, this is the largest one. And you can see its torus shape. You can see a robotic arm there that does the maintenance, because the maintenance is no longer done by humans inside. And you will see that all this outer wall is equipped with diagnostics. Okay? There are lots and lots of diagnostics to measure what's happening inside. And, well, basically what happens is that at the beginning of experiment, they puff gas into the machine, okay? They turn on the magnetic fields. The gas becomes confined, okay? It starts being hot and hotter and hotter until fusion starts to occur. And fusion does occur. The only problem is that we have to put in more power than we get out. So that's why it's still not a source of energy, okay? But JET has the record for energy production in the world. So it's the fusion machine that has achieved the highest energy production by fusion. Still lower than the input power that was needed to run the experiment, okay? Still lower, but okay. We're getting there. So just for you to have an idea of the size of the machine. So this is how the machine looks from the outside. So the torus is there inside, and then there are these coils also outside, which are important to establish the plasma current. And then you can see a person there. I have a smaller figure here for you to see the scale of this thing. The torus is about 4 meters high, 2 meters wide. And, well, as I was telling you, there are lots and lots of diagnostic systems around. And this is where we come in. Okay. Well, I've told you a few concepts about fusion. We need to know the temperature inside the reactor. We need to know the density inside the reactor. We need to know how many neutrons are coming out, right? The plasma is radiating, and then when I say radiating, don't get scared, it's radiating light. It's radiating actually an electromagnetic field in a large spectrum that goes from light to X-rays. So it's, of course, some of these spectra are damaging for us, of course. But it's just to tell you that it's radiating electromagnetic energy, so we have sensors for that. There's a whole lot of sensors. It's about 100 diagnostic systems connected to JET. Each experiment lasts about 30 seconds. Okay? I'll tell you why it doesn't last longer in a few slides. But each experiment lasts 30 seconds. And in 30 seconds, they collect 50 gigabytes of data. And they have conducted, in the last 5 years, 10,000 experiments. So 10,000 experiments times 50 gigabytes of data. Just do the calculations, and you'll see that it's a very large amount of data. So that's where we can come in with new techniques like machine learning, deep learning, to analyze these data. Okay? Because the old-fashioned physicist, I hope nobody starts throwing tomatoes at me, the old-fashioned physicist, has other techniques, of course. Has theories, mathematical background, has ways of understanding things, of really understanding, because the physicists want to really understand the physical phenomena, right? But we as computer scientists, we can provide insight by analyzing data, even though we don't fully understand the physical phenomena. Let's see how. Okay, in this talk, I'm going to simplify things, and I'm going to talk about a single diagnostic. Whatever I talk here could be generalized to other diagnostics. But this is the only diagnostic that we'll be working with today. So this diagnostic measures radiation. So I was telling electromagnetic radiation, so light, X-rays, in that spectrum. So basically, let's forget about these cameras here, but basically it has two cameras, a horizontal camera and a vertical camera. And these cameras have certain lines of sight. What does that mean? This line of sight over here is measuring the total radiation along this line. For those of you with a mathematical background, it's measuring the line integral, okay? But it's measuring, if you sum all the radiation along this line, you get a result that is being measured at that detector. So we have about 24 lines of sight from here, 24 lines of sight from there, a few more reserved channels, so we have in total 56 lines of sight. And this works, conceptually, this works very much like a CAT scan, a tomography scan. So have you ever been to the doctor to do a CAT scan, where when you get into the machine? The machine is round. The machine is round because actually the sensors are rotating. So in those machines, you have the cameras rotating around your body, right? Not happening here. Okay, this is a much simpler scenario. And by the way, in medical tomography, they use many, many more lines of sight. Here, for them, using just 24 lines of sight is ridiculous. Okay, but the application, because they want a high resolution of the inside of our body, right? But in this application, it's reasonable, and it's enough to get some sense of what's going on inside the plasma. Okay, so we get the measurements from the vertical camera, from the horizontal camera, and then there is this computationally expensive process of calculating the reconstruction, so reconstructing the plasma profile. So this is the radiation that is coming in a certain experiment at a certain time. This is the radiation that we are measuring from the plasma using these lines of sight after the reconstruction. Okay? We'll see more of those reconstructions in later slides. Okay, just to give you an idea of how computationally expensive this could be. So let's start from below. Each reconstruction could take 1 hour. Okay? I will simplify things, and I will just tell you that we should have 200 reconstructions per second. Per second. Okay? 200 reconstructions per second of experiment time, of course. Those 200 reconstructions will take us 200 hours to compute. And if we have 30 seconds, it's 200 times 30 seconds. So it's 6,000 times 1 hour would be 250 computational days. Of course, you can do this in parallel in several machines. Okay, you can divide this by a factor, but it's still days. Okay. So this is where we turn to deep learning. Now, quick slide about deep learning. Most of you have probably seen this in many places. I'll just recap the main goal here and why it could be interesting for us. So at the top, you have actually a very early work from Jan LeCun, where we had some handwritten digits, and he came up with this, well, he was also based on the work of other authors, but he came up with this convolutional network that would classify each of the input digits. You know, it would say whether it's 0, 1, 2, up to 9, right? So that's why the output is 10, because you have 10 digits. So if you feed an image, you need to have one of those results. Here is a more recent work. So actually one of the works that around 2012 triggered this whole area of deep learning, right? Where a similar network, but much larger, still small compared to nowadays, but much larger and running on GPUs, was classifying web images, right? And we could have, you can see by the output, we could have 1,000 different classes of images. So if we feed an image to the network, we would have a result saying, hey, this is a tennis ball, or this is a dog, or this is a cat, or whatever. Okay, what could be the relationship between CNNs, convolutional neural networks, and tomography? The problem that I just told you earlier. What could be the relationship? Well, the relationship is that what we want to do is the opposite. It would be great if we had a network that receives the measurements, which is 1D vector, right? Vertical camera, horizontal camera, all in one array. Receives the measurements and then proceeds in the opposite direction and gives us the reconstruction. How about that? So that's what we try to do. We just picked up the architecture of CNNs and we flipped it around. And you get this kind of, you could call it, although it's not very precise, but you could call it a deconvolutional neural network. Okay? It's a network that accepts our 56 measurements coming from those cameras, okay? Has 2 fully connected layers, and then has the reverse operation of a convolution, which is technically called a transposed convolution. It's just a matter of transposing the matrix. So what this means is that you will get here the results that if you would do the computation in the opposite direction, you would get a convolution, okay? But this is a transposed convolution, so it gives us the original values. Okay, it just works fine. No problem. No problem about this. If you pick up any deep learning framework, it should support transposed convolutions as well. And even if it doesn't, you can actually try it with regular convolutions. It will also work. Okay, so here you see 2 densely connected layers, and as is typical in a CNN, a few convolutional layers. But in a CNN, we have subsampling. Okay? In this network, we have the opposite. We have supersampling, if you want. Okay, and finally, we have also a number of filters, and at the end, since we want a single image, we just merge all those filters in a single layer. All right, so how do we train this network? So we grabbed all the experiments from the past 5 years, and the past 5 years is 2011 to 2016, because JET has stopped operation for a while they are upgrading the reactor, okay? And it will begin operation very soon, perhaps even this year, if not earliest next year, so it will begin operation again. But anyway, we look at the previous experimental campaigns, we look at all the experiments they had already run and all the reconstructions that they had already produced. And there is a total of about 25,000 reconstructions. You can guess that these took a long time to produce, right? But anyway, this was over the years. So right now we have this amount of data, and what we can do is, okay, let's split this into training and validation. You can choose other percentages. This is just an example. The reason why I'm putting the numbers here is that at some point you are going to have to choose a batch size to send to the GPU. And of course the batch size is limited by GPU memory. Anyway, to train this network you don't need a very large batch size. You can train this on a Titan X, no problem. The thing is, it's good when you're training for many epochs, it's good to feed the GPU with completely full batches, right? You don't want to send batches to the GPU and the very last batch has only 10% of data, right? That's a waste. Right? So when training this network, we try to give to the GPU only full-size batches. So that's why we came up with this strange batch size, okay? Because if you pick up those samples and you want to divide them into batches, for example, if you divide into 75 batches, okay, then you have a batch size of exactly 307. So it's an integer. Good. 75 batches, 75 updates per epoch. All right, let's see the training of this thing. So on a Tesla P100, we just let it run for a while, but it's not even necessary to let it run for more than 24 hours. You can see how the validation loss is evolving, so it gets to a flat bottom. Actually, if we let it run for longer, you will see it getting up a little bit, so clear sign of overfitting. Anyway, in this experiment, of course, we can run this as many times as we want, but in this experiment around here, so epoch 1700, we got the best validation loss. And this error is actually very small. I could go back a few slides to show you the reconstruction and the dynamic range. This error here would be a tiny bit on that dynamic range. So it's actually a very small error. It's almost the experimental error of the sensors. So nice. Okay. All right. We trained the network. I'm sorry, but I have to be a little bit closer. All right, we trained the network. So what I want to show you is the reconstruction of a full experiment. And this reconstruction was produced by the network. Okay? Let's have a look. Bang. You have just seen a disruption. Okay? You have just seen the main reason why an experiment does not last more than 30 seconds. Okay? You see there 54, but the experiment starts at 40. Okay? That's when the systems are turned on. You have just seen in this video something like this. And these are also reconstructions generated by the neural network. You have seen something like this. A focus of radiation starts developing close to the outer wall. Okay? Then it seems to disappear. Okay? It seems to fade away. But a little bit later, we see that this focus now appears at the plasma core. Okay? And stays there. And it looks really stiff, right? It stays there for a rather long time, about 1 second there, right? And then at the end, it seems, okay, things are going fine. Then we have a major disruption. So I was telling you earlier about how the plasma is not supposed to get in contact with the walls, okay? And it's difficult to say if it does get or not get, because some particles could touch the wall. And when these particles touch the wall, they grab particles from the wall. They grab metal particles. And these metal particles, they radiate a lot. It's tungsten, okay? They radiate a lot. So what we could be seeing here, of course, this has to be validated by physicists, okay? We're just analyzing the data. But what we could be seeing here is sputtering on the outer wall. The plasma is grabbing particles from the outer wall. These particles get into the flow of the plasma, and eventually they go to the plasma core, to the center of the plasma, right? And since they are metals, heavy metals, they radiate a lot. So this is consistent with a very strong source of radiation inside the plasma. However, since these particles are very heavy, okay, they do not reach as high temperatures as the lightest particles. So they are actually cold. They are very hot, okay? But we can consider them cold. So at a certain point in the experiment, we have the whole plasma, and at the core we have a set of very heavy, cold particles. What's going to happen? The plasma is going to collapse. It's hollow in the middle. It's going to collapse. And this is what happens. We have a major disruption. So what I just told you is the commonly accepted theory for disruptions. But it's not a mathematical theory. It's something that physicists have found by analyzing the experiments. These data seem to confirm those theories. So now in the second part of my talk, I'd like to tell you about another experiment that we did to try to predict these disruptions. Okay? And in principle, it should be possible. I'm going to show you why. These are the raw signals from the cameras. And you guessed it, that's the disruption. Okay. So at least we can know if a disruption happened. Right, but it's too late. So we have to look at what happens before the disruption. And aha, there is something strange going on there. Okay? So just before the disruption, the behavior of the plasma changes. And this is what physicists call a precursor of the disruption. Okay? It's a sign that the regime has changed and something wrong could be about to happen. So our idea, why don't we feed these signals to a recurrent neural network and ask the recurrent neural network to predict if a disruption is going to occur? Okay, I will be assuming that you already know about recurrent neural networks. It's not very difficult to find some nice materials on the web. I just like to highlight why they have to be so complicated, because this is often the point that people don't get. So here you have a simple recurrent neural network, and what happens is that the network actually has two inputs. It has the current sample, okay, at time t, and it has its current state. So these are two inputs to the network, and it gives an output. So if we have a sequence of measurements over time, we just provide the network with those measurements, and at each time point we have two inputs: the sample at that time point and the current state of the network. Now the problem with this architecture on top is that when you get to the very last sample, the network has completely forgotten about the first samples. Okay? So that's why Jürgen Schmidhuber and others came up with the LSTM architecture. And basically, it's a way of communicating long-term knowledge across the network. You see this arrow coming all across. So this means that at later time steps, the network still remembers what has happened long before. And this is a very useful mechanism. So this explains why these networks have to be a little bit more complicated. So in order to account for these long-term dependencies. Okay. Here is the network that we devised for disruption prediction. We are going to use an LSTM. But let's say in order not to overload the LSTM with the raw signals, we're going to use some 1D convolutions, okay, to extract some features from the signals. And then we are feeding those features to the LSTM. Okay? Now, there might be among you people who have worked with RNNs in natural language processing. This is exactly the same thing here. So in natural language processing, these 56 elements are a word in vector space, right? A sentence is a sequence of words. You apply a 1D convolution over a sentence, a sequence of words, to extract features. Okay, let's come back to our context. We have 56 measurements from the lines of sight. A long time, we can use, a large sample over time. We can apply convolutions over that sample to extract features, and finally, we feed it to an LSTM. Okay, we still have a dense layer at the end, and then we have a single node. I will come to this in the next slide. The question now is, what are we actually trying to predict? There are two ways to come up with a disruption prediction. There are fundamentally two ways, and other authors have already tried these kinds of predictions. So you can either try to predict the time to disruption. So how long do we have until the disruption occurs? This is nice, because if we know that the disruption is going to occur in 100 milliseconds, we can take preventive action. 100 milliseconds is more than enough to puff some gas, cool down the plasma, and avoid the disruption. If we can do that, it's more than enough. So this is one way to predict. How much time do we have left until something wrong happens? The other way to predict is, what is the probability that this experiment will end in a disruption? Then the idea is, if the probability gets too high, above a certain threshold, then, hey, we need to do something about it. Okay? All right, if you are curious about the details, so if we're predicting the time to disruption, this is a real number. We're not going to use any sigmoid, any activation. We can use a loss function such as mean absolute error. If we are predicting a probability, then of course it's nice to have a number between 0 and 1, and the objective is a binary cross entropy. Okay? I won't get into the details, but if you work with deep learning frameworks, you should be more or less familiar with this. Thing is, if we are predicting time to disruption, we need to have disruptions, and only disruptions, right? Because when there is no disruption, we cannot use that for training. If we are trying to predict the probability of disruption, we are classifying, right? Is this experiment disruptive or not? And then we can use all the data. So this is the main difference between the two variants. In one variant, we only use the disruptive experiments. In the other variant, we use all the experiments. Just by looking at the numbers, you can see that about 20% of the experiments end in a disruption. We can split this into training, validation, as usual. And just to make things a little bit clear, so this is a sample that we're going to use for training. And we take samples randomly. So we go to the experiment, we take samples randomly to train the neural network. Every time we take a sample, we are, if the experiment is disruptive, we are at a certain distance to the disruption. So this can be used for training, right? For training the time to disruption, this distance to disruption. If we're training the other variant, we just have to know, is a disruption occurring in this pulse or not? If it is, it's 1. If it's not, it's 0. So we're going to draw random samples, use a very large batch size, because here we are using the raw signals, not the images. So the raw signals, so the data is quite small. We can use batch sizes like 2,000, 3,000. And actually, it's a good idea because since we are drawing random samples, the training is very noisy, okay? Because every epoch is different from the next epoch. So the training is very noisy. You can actually see that the probability of disruption is actually even more noisy than the time to disruption. Okay, training. again, let it run for a P100 for some hours, not even 24. Grab the point where we have the lowest validation loss. Okay, there is some noise. It could be over here, over there. It won't change much. You can see the overall trend. It's already overfitting. And here it's much more clear. Okay, we got lucky there. We got the low validation loss, but it would be here around anyway. So on that, it's already overfitting. Okay, so now let's use these two variants of the recurrent network, and let's try to analyze some experiments in real time. Here is a disruptive experiment. You can see by the dashed line where the disruption is. So if we're trying to predict this disruption in real time, what information are the two networks providing us? Well, in red, you can see the probability. And in blue, you can see the time to disruption. So over here, we are already predicting that the disruption will occur in about 2 seconds, which is more or less right. It's more or less right. In about 2 seconds, the network is predicting we'll have a disruption. And over here, somewhere over here, the probability has hit 0.9. So we could define a threshold and say, whenever the probability hits above 0.9, we trigger an alarm and we cool down the plasma. Or, whenever the time to disruption goes down a certain level, we trigger an alarm and we could run the plasma. From our experience, it's not enough to consider one of these separately. We must consider the two of them. Okay? So we get the best results when both the probability has surpassed a certain threshold, probability threshold, and when the time has gone down below a certain threshold. When both conditions, when both conditions are true, then that's the perfect time to trigger an alarm and try to avoid the disruption. Okay, here you see an example of the disruption. Here you see an example of a non-disruptive experiment. You can see that the time to disruption is hitting 0 actually. So the network thinks a disruption is about to happen or is actually happening, but actually it's not that way. If we look at the probability is also 0. So in this case, we don't have to trigger any alarm. So this is a true negative. Again, a true negative, but here we were very lucky. Probability hits the ceiling, okay, hits 1. Probability hits 1, but the time to disruption is still rather high. Of course, here something happened there. The network thinks it's going to disrupt, but at that point, the probability is also low. So we take no action, okay? Here, the probability is 0, and the time to disruption is very high. No reason to worry. Now, let me show you some very curious results. And I bet the physicists were not anticipating this. This is a disruptive pulse. And just look at the probability. The probability has hit the ceiling and stay there practically for the whole experiment. While the time to disruption was not very certain. Here, whoa, it's dangerous, then no problem, then dangerous again. But the fact is that the probability of disruption stay there for a long time. And this is not the only case. Here is another example. Probability of disruption has hit the ceiling. Okay, some doubts over there, but has stayed, okay, just at 1. The network is telling us this is a disruptive experiment from the beginning. From the beginning, the network is telling us this is going wrong. And if you look at the time to disruption is telling us this is going wrong, this is going wrong. So the question now is, how come the network knows almost from the beginning of the experiment that it's going wrong? Well, my explanation is that the network is actually clustering. Okay? It figured out that when we use certain intensity of heating, the probability of going wrong is much higher. So we should look at these results with a grain of salt. I mean, the network does not know the causes of disruption. It just analyzes the data. And from the data, it looks like this kind of experiment, and there are several of those in the database, this kind of experiment will go wrong. Now, some other curious situations, and I'm almost finishing. Here are some false alarms. At the midpoint in the experiment, we get a very low time to disruption, and we get a very high probability of disruption. So according to our thresholds, and you can choose basically whatever threshold you want, this will be unavoidable. Okay? To a certain degree, we will never get rid of false alarms. Never. Of course, the physicists don't like this, because if they discover that the experiment was actually going well, and we triggered an alarm and ruined the experiment, they will be angry. Okay? So they don't like this. We should reduce false alarms as much as we can. But it will be unavoidable. According to all our experiments, there will always be some fraction, and could be as high as 10% of false alarms. 10% of disruptive pulses, not 10% of all the experiments. 10%, let's say, 10% of our predictions will be false alarms. 10% of our disruption predictions, so in case of disruption, will be false alarms. And this is unavoidable. There are some things that happen in the plasma midway through the experiment, and it looks like a disruption is about to happen. Now, another serious case. This is perhaps more serious. In this case, the network is unable to predict. Okay? You can see that by the time you reach the disruption, the probability was very low, and the time to disruption was very high. No way to predict. Of course, once the disruption happens, the network says, hey, disruption, right? Okay, but that's too late. That's too late to take any action. So actually, technically, we could say that we can trigger an alarm, but not with sufficient anticipation. Okay? Physicists will say, okay, this does not work. It's a missed alarm. Well, fortunately, and I had some trouble finding an example like this because they are very rare. We can reduce the false alarms to 2 to 3%. Okay? So missed alarms. Missed alarms, so false negatives. We're talking about false negatives. We can reduce false negatives to 2 to 3%. We could even reduce more if we want, but if we reduce the false negatives too much, we will have more false positives. You see, there's a trade-off. There's a trade-off between these two. Okay. Conclusion slide. You have seen the applications of neural networks to nuclear fusion, to the analysis of fusion data. We have seen that both convolutional neural networks and recurrent neural networks are useful for several different tasks. You have seen that we can use some of these in post-processing if we want to reconstruct the experiment and analyze it. We can use these in real time, and in that case, inference will be the most important aspect. Okay? So training, we can spend as much time as we want, but in real time, we'll need to have inference as fast as possible. But the amount of data is not very much, so we could do this easily on a sufficiently good GPU. And if you want to have a look at the actual code, I put the code on GitHub, so you can actually go there and see how we built these networks. And actually, there's the code there to generate a movie. Of course, there's not the original data there because that's not so simple to put on GitHub. You can also get other references, like a team from Princeton has made the news last year and also at the beginning of this year, has made the news by also predicting disruptions. So you could also have a look of the work of William Tang at Princeton University. And that's it. Thank you.